Welcome back to day 2 of the 2020 Summit on What Next for Wireless Infrastructure, hosted by the University of Surrey 5G Innovation Centre in association with TelecomTV and supported by ETSI. We start our afternoon session with a presentation from Howard Ben, VP Communications Research at Samsung Electronics, on the subject of hyperconnectivity with 6G.
Welcome. I'm Dr. Howard Ben. I work for Samsung Electronics at Samsung Research in the UK, and I'm the Vice President of Communications Research. So my role is to look at the communications technology, 3GPP standards, and standardizing that technology. What I'll talk about today is some of our vision for the future and for 6G. So it only seems like a couple of years ago that I was talking about 5G before 5G was even thought about in commercial terms. Turns out that was actually 7 years ago, and I gave similar talks on 5G as I'm going to introduce you to 6G today. 75 networks out there as of April, about 101 networks today, and you can get a lot more information on that from the GSM Suppliers Association and gsacom.com. So we've seen this evolution of technologies, higher bit rates, lower latencies, and a whole raft of additional features added with every release that we have in 3GPP. We're also seeing the time to develop standards reducing, and the commercial networks are coming out a little bit quicker for every new release that we have. That may be hindered slightly with our current situation with COVID-19. We've already seen a 6-month delay in release 17 in the 3GPP standards. Hopefully, by the time we get into release 19 and 20, we'll have caught up with ourselves again. So what are the key trends? What do we need to do differently? Well, now we've connected nearly every human being on the planet, it's time to connect more machines. We've talked about this for many, many years. IoT predictions have always been very large, sometimes I think over-exaggerated, but we're now at the stage where more and more things are getting connected, and they're getting connected over cellular as well as over Wi-Fi. That will increase over time. We're also seeing the world of artificial intelligence and machine learning coming along. It's transforming the way that mobile networks are run, operated, and planned. We are seeing more of this on a daily basis. So everything from something simple like how do I save power in my base station to how do I plan my new network and how do I work out when the network is going wrong. Open source and open interfaces, another expanding area. We've always had open interfaces within the 3GPP based technologies. Some would argue they are not open enough, and the O-RAN Alliance are looking at this at the moment and opening up more of the radio interfaces. People like ONAP are starting to do open source software for some of the operations and maintenance interfaces and some of the core network interfaces. So vast amount of work in opening those networks up. Samsung are very much behind a number of these alliances. We're working in the world where social goals are going along with mobile communications goals. So we are making our networks greener. We're working with factories and smart factories to make them more efficient, more energy efficient, less waste. Working with education, we've seen a lot of education at home recently with the COVID situation. We're generating more and more of the ability of people to do that in an efficient manner. Extended reality is the next stage for the VR technology that we've seen over the last few years. This is getting rolled out now in industry. We're seeing more and more of this. Some fascinating use cases out there. You've only got to look on YouTube and watch people driving forklift trucks. remotely, to see that this is now becoming reality. Holograms are maybe a few more years away, but the technology is getting there. I've seen a number of demonstrations now, very, very impressive. I just love the technology. I don't think it's quite commercially viable yet, but in 10 years' time, when 6G starts to roll out, it probably will be. These technologies require extremely high bit rates in order to work. So we're talking about hundreds of gigabits per second to get really high efficiency holographic transmission. Data replicas is another interesting area. So we're seeing an awful lot of digital twin technology coming along, being able to manage factories with a real factory working alongside the digital twin factory, remote monitoring, and again, the use of holographic displays, VR, XR, in order to control those factories. So all of that is putting strains on the current 5G network. So for 6G, we need higher bit rates, lower latencies. So it seems on the surface to be more of the same. And to some extent it is. We really need to have improvement in the performance of the networks. How are we going to do that? Well, what we're starting to do is, first of all, look at different architectures, different architectural requirements, the way that we can split intelligence and computing power amongst the network. We're seeing a whole set of requirements coming in on trustworthiness, especially with artificial intelligence. How do I know what decision's being made and how it's being made? So the candidate technologies that we're looking at are listed here. I'll quickly talk about some of these now. Terahertz technology, this is the frequency bands that we operate in. So we've gone from millimeter wave, which kind of goes up to around kind of 30, 40 gigahertz. It's not really terahertz, actually. It's sub-terahertz. We're talking 140 gigahertz up to about 300 gigahertz frequency band. We're going to need a whole raft of new technologies to make this work. Those two new technologies are just being developed now. We need to develop them now in order to have these commercially available in 10 years' time. So those technologies are the basic building blocks, so power amplifiers, A to DC converters, whole raft of stuff, including antennas. So for antennas, we're starting to look at different techniques for these really high frequency antennas, using metamaterials for the beamforming. We need beamforming because at higher frequencies, the range is less because propagation losses increase. So we need narrower beams to get that range back again. We're starting to see the use of reflective surfaces, so putting panels, passive panels onto walls to increase the coverage. And of course, this is where things like AI come in for the planning tools as well. Full duplex technology has been talked about again for many years. Technically, it's been very difficult to do. So we transmit and receive on the same frequency at the same time. That puts a lot of constraints on the radio because we are transmitting interference directly into our receiver, and we have to reduce that interference with interference cancellation methods. Those methods are getting significantly better over time. The technology is getting better. So by the time we get to 6G, I think this will be built into the system from day one. The network topology is changing. We're just seeing now the use of relaying nodes in 5G. IAB is the technology in 3GPP that we have developed. That allows you to both use the base station as a relay node and also serve traffic, but without having to have a fiber connection to every base station. It reduces the cost of the network rollout, and we've started to see an awful lot of that in our networks in the US. We're also seeing the use of satellite communication. Satellites, especially the low Earth orbit systems, they are starting to get to the stage now where people are putting the money behind them. We'll see how successful they are, but they provide plenty of opportunities for us for the future. AI and machine learning for communications. As I've said, we're using a lot of those techniques in the systems today. Comprehensive AI is where we bring all those technologies together. So instead of having a separate bit of AI to do our network planning and a separate bit to do our network management and a separate bit in the networks in the middle doing power optimization, we bring all of those techniques together. One of the outcomes of this will be increased amounts of spectrum sharing. So spectrum is always the limiting resource in all our systems, or it has been so far to date, probably will continue to be in 6G. The network operators are more and more willing, I think, to look at this spectrum sharing technologies. The AI is getting a lot better at managing that, making sure that we can increase performance overall. Split computing is where we look at different compute architectures for different devices connected to the network. So today, when we have a mobile phone, especially the high-end mobile phones, they have plenty of computing power in them. They can do all sorts of clever stuff. But if I've got my smart TV or my smart watch or even my really low-cost IoT device, they have less capability, but we may want to do the same things. So what we're starting to look at is architectures where for some devices, everything runs on the phone. For other devices, we start putting some of those compute technologies into the core network. And that is into both the cloud-based core network and also the mobile edge node. So when will all this happen? Well, we are looking at this technology now. We're developing some of the key elements as I speak. We will probably start standards work in the next 2 or 3 years in 3GPP. Commercial networks probably around about 2030. So just to conclude, we have now commercial networks on 5G. We're still doing technology development on 5G, but slowly we're starting to see the start of 6G research. We're starting to see this 10-year roadmap pan out in front of us, and we're working towards the next generation of hyper-connected experience. Thank you.
You're watching the 2020 Summit on What Next for Wireless Infrastructure. Our next presenter is Alan Carlton, Senior Director, Innovation Labs for InterDigital UK. His presentation is entitled B5G to 6G, a pragmatic look at what might lead us to another generation.
Good afternoon. My name is Alan Carlton, and I head up InterDigital Wireless R&D activities in Europe. It is my great pleasure to be here today to present some of InterDigital's high-level thoughts on what is next for wireless on the long road to 6G. But to start with, I would like to give you just a little bit of background on InterDigital. You may be familiar with us, but over the last year or two, we have grown quite significantly. InterDigital is perhaps best known as a wireless R&D organization. This remains very true today. Here, our interests remain very broad, covering all aspects of 5G and what is becoming increasingly referred to as beyond 5G. Video technology, as we prefer, visual processing technology has also been an area that we've had a long interest in, but historically at a much reduced relative level. This is, however, no longer true. With the acquisition and merger of the R&I division of Technicolor, we are now very much a wireless, networking, and visual processing organization. Internally, we like to joke that prior to this acquisition, we were in the business of solving the future problems of wireless, but today we're also very much in the business of creating those problems too. Joking aside, this merger really does provide us with something of a unique perspective and all of the intertwined roadmaps that certainly go beyond wireless, but will inevitably shape what we will be required to support as a wireless industry in the future. One of the first questions I always get asked on the topic of 6G is, what is going on and where are all the ideas for it cooking? The simple answer on this, there is quite a lot going on. A standards discussion is still quite a ways away, but the industrial research and consensus building phase is in full swing, just like it was back in 2010 for 5G. InterDigital is involved in a number of areas, including some quite futuristic collaborative projects in the terahertz space and other areas. We're also involved in a number of ecosystem thought leadership activities like 6G Flagship in Europe and the Power and ATIS Next G Alliance initiatives in the United States. We see all of these as consensus driving initiatives that in time will serve to shape the definition of 6G and the requirements the industry will agree that will drive it. So what do we need to get to an XG? I have been working in the wireless space since 2G, and like some of you, I'm sure, I have lived and worked through the inflection points across 3 generations now. Every generation change has roughly shaped up the same way, and at this time we see no good reason as to why 6G, when it comes, will be any different. Every new generation requires 3 essential ingredients: something new, as in a new service of some sorts, something broken in the sense that the prevailing generation can no longer efficiently support the new requirements, and critically, more of the same, insofar as the new generation must make the core services of the previous generation work much better. I do not think any generational switch characterizes this more than going from 4G to 5G. Much has been talked about the 3 so-called services in 5G, but of course they are eMBB, URLLC, and massive machine type communications. But we had mobile broadband in 4G, and 5G is certainly bringing more to this. 4G also certainly opened the door to machine type communications, but let's be fair, this door was opened in 2G, but it just took us to 4G to embrace it with the invention of the myriad of IoT radios that have been defined over the last decade. So similarly, it is fair to say 5G is bringing much more to machine type communications. Seen through this lens, the only thing that is really genuinely new in 5G, in my opinion, is what will be delivered under the service umbrella that is the URLLC label. In terms of what was broken in 4G, evidence suggests that it was not really the radio. OFDM is still here and will quite possibly persevere into 6G too, at least in the lower bands and some new flavors, perhaps. The broken bit in 4G was in fact the general overall system architecture. This was the real issue, as it was simply not flexible enough to evolve much further under the weight of the growing service requirements. We expect the beyond 5G to 6G path to shape up in a similar way. From the 10,000 feet, this is how we see it. B5G, 6G will be required to reach a much wider set of use cases and market diversities. We're already seeing the beginnings of this with features like NR Lite in Release 17. Without going into it, this feature addresses the use case that does not fit neatly and tidily at one of the vertices of our classical 5G use case pyramid. We expect to see a lot more of this, and we expect this to push the real flexibility capabilities of 5G over time. As I will get into a little bit in the next few slides, 5G simply won't support the real extreme requirements of many of the use cases that it will simply open the door to. In terms of a new service, all I will say is we do not expect it to be so new that it will emerge to enable some new or much improved convergence of our physical and virtual worlds. This will likely begin in 5G, but it will only be achieved at a true immersive scale in 6G. In this way, the service may be perceived as new to the consumer. At InterDigital, we have referred to this convergence of the physical and virtual world as creating a living network for the last 10 years. 5G will certainly be a major step on the latter stages of this roadmap. And looking forward, the convergence of wireless with other technologies such as AI, ML will be key to completing this vision. But it will probably take to a 6G to deliver it at true scale. Again, this is not terribly different than the relationship 4G had with 3G. When looking at emerging use cases, we see 5 principal categories driving evolving wireless requirements. The first takeaway is perhaps that these use cases look very familiar. After all, didn't 5G promise all of these? The real takeaway on these use cases, however, should be that these one-liners that we have all seen splash so many times in front of us, in different forms sometimes, conceal long and rich roadmaps in themselves, some of which will only be scratched by what 5G brings to the table. If we look just a little deeper at one of these use cases, multi-sensory extended reality, XR for short, it becomes clear just how complex these independent roadmaps are. In our view, XR is certainly the leading contender for the next personal mobile compute platform with smartphone-like evolution potential. And we certainly need it to shake up the smartphone form factor just a little bit. The challenges on this roadmap are, however, immense and have dependencies that go well beyond wireless and visual processing, suggesting that there will be many point product releases here over the next 10 years. One thing is clear, however, that the specified 5G average user experience data rate of 100 megabits per second downlink and 50 megabits per second uplink will need to grow quite significantly, possibly an order of magnitude or more, in order to deliver the perfect immersive experience at truly significant scale. This roadmap requirement justification alone may take us to a 6G. The XR use case is certainly not the only requirements roadmap that will push 5G. We have examined the extremes of the other use cases, and this heat map highlights and shows just how 5G will be pushed across a range of KPI over the next 10 years. Some may be addressed to some extent in 5G, but it would appear more likely that we will need some new generational shift to satisfy them all over the longer term. Looking now to some of the emerging technologies, solutions to these challenges on the wireless roadmap, I want to just highlight a few that we see the potential over the longer term to challenge the status quo of 5G and possibly create inflection or breakpoints that might take us to a 6th generation. There are certainly others too, but these 5 are the ones that I would put my money on today. I do not think any one of these will do it by themselves, but again, as history tells us, it is generally an accumulation of many factors that is required to create a generational shift. And more, it is how the fusions of these individual roadmaps play out together that actually shape what the future eventually turns out to be. The first one is what would seem like the inevitable and somewhat obvious push into ever higher spectrum bands and new sharing models. This push today is perhaps most interestingly highlighted in 3GPP with the embrace there of an exploration of spectrum above 72 GHz. This is something that 5 years ago would have been thought impossible on a forum like 3GPP. If we continue this trend line, as would seem inevitable, then fundamental problems start to appear with digital design and OFDM methods above 100 GHz. While I would think OFDM, or maybe a close, perhaps a bit more energy-sensitive cousin, is safe but not necessarily certain in lower bands. As we move into higher bands, we will certainly need to move to a simpler waveform to account for the many challenges that exist there in RF circuit design. Altogether, this might create an inflection point in 5G sometime in the future. Another perhaps obvious one, on the surface at least, is wireless AI fusion. There's a lot of hype around this area now. I think the application era we are living in today is much more about finding out where these fusions don't make sense, as it is about where they do make sense. The focus today is really in higher level network functions, but this will push a lot deeper into the RAN and later into the design of future radios. Not least of all, AI/ML may provide the solution to the non-linearity challenges in the terahertz systems I just mentioned. Over the long term, as our nodes all become more intelligent, then this might lead us to whole new approaches to protocol and radio interface design. I doubt it will ever replace traditional design, but this impact could prove significant in time to create another significant inflection point in 5G. Another hot topic is reconfigurable intelligent metasurfaces. There has been great progress here from a core technology perspective. This interests me less than the longer-term potential that lies here to inject a whole new node into the wireless system, revolutionizing how we might view the channel in the future. This could be a final frontier in network softwareization, turning the radio channel into a software programmable entity too. Progress here may shake up traditional RAN design in the future, creating another possible architectural inflection point. We will see in time. At number 4, we see another paradigm shift gradually emerging, that is from our devices simply being wireless information transfer devices to being generally wireless information and power transfer devices. This is all part of what we are seeing as a more holistic approach to spectral and energy efficiency driven design emerging. While this is unlikely to drive a new generation shift by itself, it is another element, when compounded with the rest, that could over the longer term have significant impact to the design of the elemental blocks in the air interface. The last one is interesting, and is one I would say I'm personally most immersed in various ways. If I were to describe 5G in one simple abstraction, it would be that it is the convergence of telecom with IT. And this is all embraced by this virtualization to cloud native, edge native roadmap. However, the billion-dollar question is just how far will we go in this journey in 5G? We've made good progress in the core network with a service-based architecture approach that has been embraced, but is arguably somewhat stalled at the moment. We're making good progress in the RAN through what seems like countless industry initiatives, but not everyone is 100% on board, and nothing in any of them is what I would call cloud native quite yet. For all the talk of network slicing, there is really no such thing as a true end-to-end network slice yet that spans the core, the RAN, spectrum, and device. There are truly big innovation opportunities here, but the technology barriers may be small compared to the business model, regulatory, and IPR barriers we need to get through first that will allow all the technology innovation that is possible here to come through. In my opinion, it might take the entirety of 5G to work through all of these, and as an industry, we may need a 6G to go all the way technologically here because of it. So, in terms of some takeaways, today we are certainly very much in the early stages of the rollout of 5G, and we do still have a very long way to go with the evolution of this technology, so none of us should be getting overly excited yet about the prospect of 6G. Still an awful lot of work to be done in 5G. That said, now is historically the right time to be asking what is next, and it is fair to say that the path ahead of us appears to be quite rich. The emerging use cases for beyond 5G, 6G may seem quite familiar, but hide a truth that 5G may only open the door to these roadmaps. Extreme requirements will continue to push the evolution of wireless well beyond 5G, and in time will enable a new service experience. Looking out to the future and the promising tech trend lines, it does appear that there will be inflection points, breakpoints in the future that may drive us to needing to develop a next generation 6G technology standard. Finally, I just want to let you know about a new resource in the space of 6G that you might find interesting. Last month, InterDigital, in partnership with Northeastern University in the US, hosted a virtual 6G symposium event under the independent brand of 6G World. The associated website is now live, and the plan going forward, in addition to 6G event planning, is to track everything 6G. over the next 10 years. So please drop by and take a look sometime. That's the end of my presentation. Thank you for your attention.
You're watching the 2020 Summit on What Next for Wireless Infrastructure. Mikko Uusitalo, Wireless Advanced Technologies at Nokia Bell Labs, is next with his 6G perspective.
Hi, I'm Mikko Uusitalo, coming from Nokia Bell Labs, Finland, heading a research department there, looking at future radio technologies, and 6G then strongly on our portfolio. So I'll be happy to tell you more about our views on 6G. So what the future communications will look like in 2030, so the expected time frame for 6G when it will really kick in. Smartphones have been serving us really well and expected to serve us well. But if we want to take the maximum benefit out of the interaction with the combination of digital, physical, and biological worlds, so we need to look at more richer interactions. For example, ways of integrating input-output to textiles, skin-patchable devices, or even body implantable devices. The last one mainly for people with impairments and people with fully functioning senses and muscles. The senses and muscles are usually a very good way of interacting with our environment, but also maybe in some time frame for them as well with these body implantable devices. What else are we looking at? Mixed reality telepresence, how to be in a maximal way interacting with others, no matter about your physical locations, using mixed reality, using the combination of physical and digital worlds. For this, we need high resolution mapping. Then how to augment our intelligence. So as individuals, we are rather intelligent. As a society, we can be much more intelligent. And then by combining also the possibilities of intelligence by machines in the best way to serve us, how can we make best out of all of these opportunities? Also, the machines can be operating autonomously. We can benefit from automation and how to make maximum benefits out from that. Then other examples, thinking about traffic. In traffic, we are already seeing quite much movement towards autonomous driving. And if we can get data from all the vehicles in high quantities and make best use of that, also get additional sensing information via communication, via other means, and make maximum use of this. And as in traffic, the speeds can be relatively high, so also how to do this with low enough latency and high enough reliability. So there are challenges here that cannot yet be met. Also, mixed reality co-design. How could we enable people in different locations interacting with each other, interacting with mixed reality, interacting with the digital worlds, while having efficient human-machine interfaces, using all of their senses, making maximum use of this virtual and mixed reality. How can we kind of make all of this happen in the best possible way? So then these worlds, biological, digital, physical world, so they all need to be connected in an efficient way. This biological world, mainly from our perspective as humans, how can we control via efficient human-machine interfaces the physical world, and how can we maintain a good model of us in the digital world to make additional benefits, for example, for some health-related applications and services. And then how can we combine in the best way physical and digital worlds? So we already have digital twins building models of the physical world. How could we enable that to be taken to a new level by having very high amount of these models, digital twins represented in the digital world, and having a kind of high amount of data online, very low latency synchronization between these worlds with high reliability. So how could we do that in a very massive way, enabling us to be more efficient in controlling, operating the physical world, and for example, then predicting any maintenance needs and so on. Then around this triangle, there are some essential components for 6G. Ubiquitous computing, how can we connect this computing? Knowledge systems, the maximum use of ever-improving machine learning and artificial intelligence. How can connectivity technologies be used for sensing? What other sensing capabilities needs to be combined here? And then this human-machine interface, enabling this efficient link between the biological and physical world. So how can we use all of this for 6G to unify the experience across physical, digital, and biological worlds? What are then the resulting requirements for technologies? So throughput capacity has been there as a basic requirement for all the generations, and we need to look for further improvement in this domain. And latency reliability has been in the focus for 5G. How can we move forward here, for example, then to fully enable all possible use cases with low enough latencies for example, automating some machine tools, and then the increased reliability is always of benefit. How can we continue improving the scale and flexibility, this precision, other kind of sensing, and with the increased use of AI, ML, how can we guarantee that when we are using these systems, so how can we drive down the adaptability response time to be fast enough to react when there is need? Then on devices, how can we push their energy efficiency maximally low, but also at this whole future communication systems, how can we there push the energy efficiency low? How can we have the future systems as sustainable as possible? And how can these systems also be used in other areas of life, then to help there with sustainability and energy efficiency? So always in the generations we have been interested for getting additional spectrum, getting more capacity, and we have been interested in how to use this spectrum as efficient as possible, and how to use the spatial dimension to increase the performance, for example, adding additional amount of antennas. On top of these 3 dimensions, 6 dimensions here in total, so 3 additional dimensions to pay attention to: increasing amount of data, how to maximally use this, also getting the sensing information and addition to communication, this computation to enable the AI, ML, and to compute based on all of this data, and the increasing needs for sustainability and energy efficiency. So what are the 6 key technologies for 6G? Been mentioning the AI, ML already several times. New spectrum technology is going to even higher spectrum to enable even higher capacities, but also need to pay attention to these mid and low bands, then how to get maximum benefit out of that to be more efficient than in using that spectrum and more flexible. This sensing I've mentioned several times, expecting further improvement and benefits, efficiency improvements in this RAN core convergence. Extreme connectivity, referring to this pushing the boundaries envelope of this low latency, high reliability even further. And as increasingly the different aspects of life get digital and wireless, so the ever increasing need for security and trust to be absolutely taken care of in a maximum way. So a couple of more words on this AAML. So it is an ingredient there to improve our operation already in 4G, 5G, but now with 6G we have an opportunity to build a new generation with having this AAML being taken kind of into account right from the start of planning the next generation. how to optimize here with end-to-end learning, how to have custom solutions for specialized environments, and for example, then how to adapt to hardware impairments. So we are looking at 6G to unify the experience across the physical, digital, and biological worlds with main ingredients, main technologies to help us there. This ubiquitous computing, artificial intelligence, knowledge systems based on this, these sensing capabilities, multisensory rendering, using all the sensed information to build the models and get the maximum efficiency. So how to use AI to optimize their interfaces, how to use the networks as a sixth sense, these extreme networks pushing the boundaries of reliability latency, new spectrum for more capacity high bands, but then also low mid bands more efficiently, more intelligently used, pushing RAN core convergence, sub-networks, so having multiple devices on ourselves or with some machines, forming like a sub-network locally, and then with the master device connecting to the rest of the network, and then how to make absolute guarantee of the trust, privacy and security. Thank you.
Next, we welcome back Regius Professor Rahim Tafazoli, Head of ICS 5G IC at the University of Surrey and the organiser and host of this event, to present his 6G vision for 2030 plus.
Hello, I'm Rahim Tafazoli, Director of Institute for Communication System and 5G Innovation Center at the University of Surrey. I would like to use this opportunity to share with you our future research strategy and direction all the way to 2030, as well as sharing our, I believe, unique vision approaching 6G. First, I would like to share with you some history of the 5G Innovation Center and some of our achievements. We started in 2013 with 8 founding members, and then the membership grew over the time, representing different aspects of the ecosystem in telecom and vertical industry. Our job working with industry is very simple. It is to demonstrate what is the art of possibilities in all aspects of 5G, on the radio side, on the network side, on the service platform, as well as application of the 5G to different vertical industries. I would like to share with you some of the highlights of the world's first achievements that we delivered over the last 7 years. We developed the first 5G core and 4G core, all virtualized and sliceable and 3GPP compliant, which is capable of hosting more than 1 million users. The first 5G private network. On the massive MIMO, I believe we achieved the world record of 5 bits per second per hertz per antenna elements. And we developed the algorithm and we demonstrated the performance. The first 5G remote controlled driverless vehicles over a distance between Guildford campus and London Excel exhibition, which is a combination of the fiber and 5G wireless. Remotely controlling a robot using ultra-reliable, low-latency communication of the 5G, and also transmitted the 3D holoportation real-time transmission using 5G technology. We tested 5G over geostationary satellite and recently over non-geostationary very low Earth orbit satellite, end-to-end testing of 5G, including our core that we developed and the service platform, and we demonstrated 4K video. And also we demonstrated and introduced 5G in a manufacturing setting for smart manufacturing. In February 2020, we wanted to celebrate our great collaboration and achievement with our industrial members in a fantastic Buckingham Palace, hosted by Duke of Kent. And also, in addition to celebration, we committed to carry on and continue collaboration for future years. From the research direction point of view, what are we going to be doing? We are going to be taking two parallel approaches. The first one, which we started in 2013 on 5G, we carry on evolution of the 5G with over the next 5 to 6 years. In 2019, we already started research on 6G technologies, and you will see some of the demonstration of that one later on at the end of my presentation. And we carry on the research in parallel with 5G evolution on 6G with our unique approach for the next 10 years. On the 5G evolution, we will try to apply and optimize the 5G technology to many vertical industries like logistics, transport, manufacturing, gaming, utility, as well as health, mainly focusing on mass connectivity, reliability, and low latency aspect that 5G provides, which we believe it will enable digital transformation of many industries using our connected vehicles on our campus testbed, as well as the UAV, all enabled with 4G and 5G technologies. On the network side, we try to make 5G as intelligent and self-organizing as possible, utilizing the rich fabric of connectivity and data from 5G, utilizing advanced artificial intelligence algorithms. For this, we are looking at applying AI to NFV layer, SDN layer, as well as the radio layer, and collect the information, process the information, and provide intelligent decision into the network orchestrator for self-management and self-optimization. Our research over the next 10 years, we are adopting completely unique and new approach to 6G compared to previous generation systems. And that has been decided in collaboration and discussion with our industry members. And this unique approach is we start with a clear use case, with a clear business case. We will not set any target KPIs in terms of speed, latency, etc. That will come as the result of research. We'll consider 5G capability of rich capability of 5G as well as its future evolution. We'll consider social and industry challenges that we are facing in terms of productivity, sustainability, and digital divide. So what is this unique approach and what is this use case and a business case? If we look at the evolution from the media perspective of the wireless technologies over the generations, we start with 2G and text and ringtones, all the way to 5G, which provides 3D video, virtual reality, augmented reality. So with 5G, it enables virtual and physical world. Either you are in a physical world or you are in a virtual world. In 6G, we are thinking about a 4D video, and the fourth dimension would enable interactions between virtual and physical worlds. And that would enable fusion of virtual and physical worlds through these 4D video. And that provides communication together with intelligence from this ambient and environment. And the fourth dimension is this ambient information. Part of this ambient information is human senses. And if we transmit human senses with holoportation, as you can see in this video, we enable a kind of teleportation. And this was, I presented this idea in 2015 in a TED Talk. And ever since then, we've been trying to look at the technical requirements and implication of delivering teleportation. It would enable the fusion between virtual and physical world, but in an interactive manner, like Kingsman film, as you can see, which is provide multi-party physical and virtual interactions. Or it can be interactions completely in a virtual world, like Star Trek. But we need to first understand the difference between latency and synchronization. 5G is capable of low latency of 1 millisecond on the wireless side, but only for a single flow. Synchronization is a time difference between different flows or different sessions generated by different objects that need interactions with each other in a real time. Objects could be 2 or more robots or people collaborating with each other in a physical world, or it can be in a virtual world, which enables many, many different applications. 5G was not designed with guaranteed time synchronization in mind. So far, I discussed about time synchronization, importance of time synchronization for interactive, virtual, and physical world application side. However, time synchronization as well as frequency synchronization become very important on the radio side in terms of capacity and the coverage. For example, in a multi-cell TDD, which is part of 5G, as well as multi-operator environment, time synchronization would reduce substantially the guard time and between different operators, the guard bands, and while we can manage the interference better. In the future system, which is a distributed MIMO for 6G in a cell-free architectures, all distributed MIMO systems, they need to collaborate and cooperate with each other as if they are all co-located. And for this, tight time and frequency synchronization become very important. Also, it will help faster spectrum sharing at even packet level. It will transform the applications that was enabled through low latency and reliability offered by 5G for connected vehicles, manufacturing, games, entertainment, as well as health. It will bring it to the new level and make the cooperative driving with low latency and time synchronization possible. So the cars can move at a high speed but all are synchronized with each other. Cooperative manufacturing between people at different geographical location in form of virtual reality as well as physical reality, or between people and robots. It will bring new dimension, a new generation to the future entertainment and games. And if you consider more the telecare and healthcare makes it more interactive, and imagine that the doctor will be virtually present at your home and he can touch your hands, your forehead for the temperature, and provide that real human-like interactions with the patients. And that synchronization is important not only in a small geographical area or a small environment, but people and robots can be from different locations all over the world, transmitting different senses, which is 5 human senses, and providing collaboration and synchronization between themselves for the natural interactions. Also, in an industrial setting, if the robots want to collaborate with each other, the important aspect, in addition to synchronization, time synchronization, is low jitter in the synchronization. Because if we don't take care of the low jitter for the 2 robots collaborating with each other over the time, because they exert different pressure on top of each other, they could crash each other after some time. So not only time synchronization is important, but also jitter becomes very important. Time synchronization and time jitter was never been part of the 5G specification, and it is beyond 5G capability. Hence, that's why we refer to it as the 6G. And that is to provide multiple and synchronized flows from different geographical locations in an interactive manner. The interactions demands tight time synchronization and time jitter. And as the objects, whatever, human or robots or whatever, they're not going to be static. For the natural reaction and interactions, we require high resolution and real-time geolocation tracking and geolocation updates. We think that the future communication will be an integration between communication as well as sensing. And for 6G will consist of 3 main subnets. One is the wearable networks, the networks in a short range communication, capturing the senses and ambient information. For communication is cellular networks, and for open areas to minimize the digital divide and enabling many of the Industry 4.0 applications, we need satellite communications. And we are researching towards a system that appears one system from the user's perspective, whether it is under the satellite coverage or indoor or outdoor environment. And we are looking at developing MIMO into space to provide direct communication to user equipments. To have a similar analogy as we had in 5G, we have come up with this triangle shape for 2030 plus, and we believe that we need to all focus our research towards a better coverage and ubiquitous coverage and time synchronization and high quality time, frequency, as well as jitter, and geolocation, dynamic and real-time geolocation determination. So All of this, together with whatever artificial intelligence will enable us to make it as automated as possible. Our mission, in collaboration with industry, will carry on, will continue to do art of possibilities and share that information with our industry partners. At the same time, collaborating with our industry members, doing advanced research and testing and demonstration. As I said, in integrated communication and sensing, we start with 4D video. And we work on integrating sensing in the communication and work more on the enhanced edge and the user environment. And underneath, there is a number of enabling technologies we have identified, like MIMO in space, direct satellite to user, large intelligent surfaces, ultra-massive and distributed MIMO towards cell-less or cell-free architectures, as well as new other technologies that we are going to undertake, and some of them we already have started. To enable 6G vision, as I presented, we need to work with other disciplines, especially other disciplines working on the new innovative materials, providing synthetic biology, and bring that one into fabric of the communication system. All of this has detailed and captured in form of our 6G vision and research challenges that we have already started and we will be taking on for over the next 10 years in a white paper that is officially available publicly and can be downloaded from our website. And officially, I take advantage of this opportunity and this summit to announce the launch of 6G Innovation Center that will run and operate in parallel with 5G Innovation Center. We didn't talk very much about capacity, coverage, and energy efficiency. One 6G enabled technology is intelligent surfaces. And I would like to show you through a video, I believe the first operational large intelligent surfaces that is being built by Dr. Mohsen Khalili, which is a lead academic at 5G Innovation Center and 6G Innovation Center, together with his team, Dr. Ali Araqi, Mahmoud Safai, and Vikran Singh. Thank you very much for your attention, and I hope you enjoy our large intelligent surface demo.
Having a good and meaningful coverage is still a big challenge for all network operators, especially in a dense urban environment where the presence of a large number of buildings and infrastructures gives rise to harsh propagation condition for electromagnetic waves, leading to lack of seamless connectivity. The major reason behind this issue is a lack of control over the propagation environment. So in this case, the propagation environment remains unaware of various communication processes going through it. The engineered metasurface is a key to make this such passive environment smart. So these engineered metasurface, also known as large intelligent surface or reflecting intelligent surface or even hypersurface, can enhance the meaningful coverage by sensing the environment, recycling the existing electromagnetic wave and redirecting them toward the direction of interest.
By these structures, you can have a control on the reflected waves, and this is the beauty of these metasurfaces. we can control something that we literally cannot see.
You come across certain places which are called as coverage blind spots. You don't have coverage over those places. And to put up a new base station is quite expensive just to cover a small area. But with these kind of intelligent surfaces, you can cover those blind spots, ensuring that the user always has a seamless connectivity, even if it is moving.
As far as I know, this is the first demonstration in the whole UK.
This is our first scenario to find out the performance of the static metal surface. This is our receiver.
So we are streaming a video here over the 3.5 gigahertz band using software-defined radio from the base station to the UE. The base station is kept here and the UE is kept inside in an area where there's a coverage blind spot. But once we place our surface at the right position, the UE will receive a strong enough signal to decode the video stream and the video will play smoothly. So now I will start transmitting the video stream from here towards the meta surface.
And this process is done by this reflecting metal surface. There is no line of sight from the transmitter and this receiver. If we move the surface, we lose the video. And now my colleague is moving the surface. As you can see, the signal is actually lost.
At 6GIC, we have developed a dynamic version of this meta surface. This meta surface is quite different from the one that you just saw. The previous one that you saw was a static version, which doesn't require any power at all, and it works completely on its own. This one requires a controller. This can actually make the beam change its angle so that the coverage always follows the user and the user has a seamless connectivity.
So just let's try. If I press the reconfigurable mode, you can see now we have video there at the user terminal. My colleague is going to move the user toward another point. Again, you see the video stream is not getting decoded successfully. So now let's again use the reconfigurable mode and let's ask the meta surface to reconfigure itself. Now you can see we have received video because the meta surface reconfigure itself toward the new position of the user equipment. In the last scenario, we are going to demonstrate the capability of our dynamic meta surface to change the angle of the reflected beam continuously to follow the user as it moves, ensuring the seamless connectivity to the user. So let's try it with the tracking mode and let the meta surface to start follow the user.
In reality, it automatically do everything. Means detect the position of the user, change the beam, calculate based on the algorithm, and do everything automatically. That is very, very big achievement for the University of Surrey. We don't have anything similar in the world. In this size and these solutions means totally together, I think we are the first one.
You're watching the 2020 Summit on What Next for Wireless Infrastructure. Our next presenter is Dr. Leon Lobo, Head of the National Timing Centre at the National Physical Laboratory, with a presentation on resilient time for future comms.
Hello, I'm Leon Lobo, and I'm Head of the National Timing Centre at the National Physical Laboratory in the UK. The National Physical Laboratory is the UK's National Measurement Institute, and we're responsible for traceability to the SI. So we provide the primary standards that provide traceability to the second, the kilogram, the meter, etc. And in this case, I'm going to talk about time and why it's important for our current digital landscape, but what we are doing as well to secure it for the future. Now, in our current crisis, and I hope all of you are well in this, we have an increasing dependence on a rapidly evolving digital landscape. I mean, just the fact that this conference is being held virtually rather than face-to-face is testament to that. But our digital way of working is going to endure well beyond this crisis. As well as that, all the emerging applications that are being accelerated, like this comms piece that we are discussing today, but also things like drones for delivery, autonomous vehicles on our roads, smart cities, wide area IoT, sensor networks, and the like, are all going to rapidly progress. But in order to ensure that we protect those and secure those as they are developed, we also need to consider what their dependencies are, particularly on things like position, navigation, and timing, as well as the threat landscape that affects these. There's a whole host of solutions being developed to help support that case and put in place alternative solutions. And we'll be talking about one of these now as part of the National Timing Center program. So our dependency across critical national infrastructure is quite significant from the point of view of our reliance on global navigation satellite systems, like GPS, for example. And that's the case, as I said, across these sectors. But what is also of real importance when we look at how we secure these capabilities is what the interdependencies are. And the dependency on comms is very widespread across pretty much everything that we do on a daily basis and across these sectors. Now, this dependency was highlighted in the Blackett report on satellite dependencies a few years ago. But what it also raised, which was more important, was that there's a lack of awareness of the dependency on the satellite signals in our infrastructure. The London Economics report that's on the left there raised the fact that should we lose global navigation satellite systems, we would lose £1 billion a day to the UK economy. And that's quite significant to consider. Now, time really is an invisible utility for a lot of our digital landscape. It tends to fall into the gap between the cyber and the physical, but it is underpinning our comm systems, so our networks of today, our energy sector for phase synchronization of the grid, our finance sector for time traceability, for regulatory compliance, but also defense, security, space. It covers a lot of capability, but it is almost always not considered because it's a signal that falls like rain from the sky, and it is very, very cheap to implement a GNSS receiver. But we need to consider where we've got that in place and start to protect that. But what I'll be talking about today is not just about the protecting what we have in place, but also considering what could we do if we were given better time and frequency signals. And that's what the National Timing Center is all about. It is about the resiliency piece, but also being able to provide this next generation capability by providing better signals to our infrastructure. So at NPL, as mentioned, we not only provide traceability to the SI, and we've got a whole host of developments for the redefinition of the second, developing the next generation of atomic clocks and the like. But we also manage what is UTC NPL, which is the national timescale. UTC being coordinated universal time, the global timescale. So at NPL, we have a whole suite of atomic clocks that contribute to the global timescale formulation, but we also disseminate that to the UK. And what we're doing now with the National Timing Center is securing that capability, but also providing those signals beyond what we do now over RF broadcast, over the internet, over fiber in the ground, as well as SATCOMs, by providing an extended capability which is much more secure and resilient for applications of today, but also future applications. So to that extent, with some of our government partners, we've been looking at what ought to be done within the UK on that front, and what those user requirements are. So whether it is, as I mentioned, for low latency comms, for synchronization of 5G networks, for better spectrum utilization, but also what could we do in the future, for example, with 5G potentially disseminating time references over those signals that are broadcast. And those are the elements that really we are starting to engage across industry, across government, to start to consider how we could leverage better timing and how we could deliver better timing based on what is in place across the board. So this program is a 5-year program. We've got about £36 million to develop this capability, and it's being delivered with other government organizations. And the primary aim really is to support our critical national infrastructure for the future by developing the capability around resilient time in the UK. So we've got 3 primary objectives for this. One is about resilience and securing what is the national timescale as it stands, so UTC NPL. We've got an innovation objective, which is being delivered with our partner Innovate UK in government. And that really is about stimulating the supply chain for timing, frequency, time dissemination solutions towards generating new products and services for the UK. And then we've got a final objective, which is around skills, education, and training. And to that, we are assessing what is in place and addressing the gaps by putting in place training courses, degree level modules, PhD studentships, apprenticeships, secondments, and the like, to support industry, ensure that they have the skill sets coming through the door rather than trying to upskill and reskill personnel, which is almost always the case to date. So from that resiliency perspective, what we are doing is putting in place what we term as RETC, which is our resilient, enhanced timescale infrastructure. And what that is essentially an enhanced capability from what we've got at NPL today, but putting it in place over a geographically distributed set of sites, which are secure and meshed such that we are leveraging multiple modes of dissemination. So including fiber in the ground, including SATCOMs for two-way satellite time and frequency transfer, as well as GNSS, in order to ensure that in the event that any one site went down, we'd still have a national capability. And we're doing it by putting in place those multiple modalities because they don't have common failure modes. And we can leverage that towards a resilient capability for the future. All these sites will be contributing to the global timescale and to the BIPM, which is the Bureau of Weights and Measures, which is the umbrella organization for the national measurement institutes like NPL. They formulate the global timescale, and then the real-time realizations are the likes of the national labs that disseminate it to the nation. But just managing the national timescale is not sufficient. It's about really that dissemination piece. As I mentioned, to date, we disseminate over RF broadcasts, over the internet, over dark fiber into the City of London, but also leveraging GNSS for some more bespoke implementations. What we'll be doing as part of the National Timing Center program is putting in place R&D nodes on a sector-by-sector basis, disseminating time and frequency references to these nodes, but shaping them with industry to structure the level of capability required for these references, but also things like the interfaces, the holdover requirements for that sector, such that beyond the 5 years, we can then pick and place and scale up this capability where it's required for infrastructures across the board. So we'll be doing that for the comms sector with the 5G Innovation Center in Surrey, We are looking at doing that for autonomous vehicles, for quantum, for potentially for energy, and look at working with you to shape what is required, not just for the applications of today, but for the challenges of tomorrow. And from the skill set, what we've done to date is engage directly with industry and academia, but also put out surveys to understand what those gaps are. And based on those gaps, what we are doing now is putting together a training blueprint, which will then inform the training courses, the secondments, the degree modules that we'll be putting in place with industry, with academia, to support the UK community essentially have the right skills in this area of timing and frequency. And that's primarily it. So really, I want to reach out and ask you to engage. We've got the links there as well as the email addresses. Please do contact us. Tell us what you feel as your pain points as it stands, but also consider what you could do with better timing if you had the references, those signals for future applications. So it's not just about making what is in place much more resilient and secure, but also considering the element of better signals and what they could offer in terms of disruptive applications of the future, based on better synchronization, better spectrum allocation and utilization, but also being able to monitor and control low latency applications as well, and low latency networks. That's it from me. Thank you very much, and please do engage.
That concludes the afternoon session of presentations for day 2. But don't go away, as we'll be back in a moment with our second live Q&A panel, your final chance to ask questions to our presenters. And I'll be joined once again by co-chair Dr. Mike Short, Chief Scientific Advisor for the UK Government's Department of International Trade. We'll be right back.